Hello, this is Mr. Pruitt, and today I'll be talking about one-dimensional kinematics. Uh, Remember that we're still talking about kinematics in terms of only going in one direction, either up and down, or right and left, or forward and backwards. But we're not really talking about it traveling in any of those simultaneously. And so when we're looking at this, we've been talking for a while about using graphs to describe motion. And so, what happens if they don't give us a graph? Is there a way that we can describe all that motion that we've been talking about without using a graph? So first, a little bit of review. Remember that there's a lot of information that can be found in the graphs on the left. Like in this velocity time graph, you could find the object's acceleration for different segments of its trip. You could find its position. You could find how fast it's going. There's a lot of different things that you can find here. In the position versus time graph, we can look at the shape of it and know whether or not it's accelerating. We can calculate the slope of it and figure out how fast it's going. We know where it is. There's a ton of information that's covered in these two graphs. But again, the question is, what if they don't give us a graph? Well, we already know that you could use the two mathematical definitions that we gave you, the one for speed, which said v equals d over t, or the one for acceleration that says that acceleration is equal to the change in speed divided by the change in time. Unfortunately, uh, the usefulness of these equations is somewhat limited. What happens if it's already going a certain speed before it starts to accelerate? What happens if I want to know the distance while it's accelerating? There's a lot of different things, a lot of different situations that can come up that these particular definitions don't necessarily address very quickly. But on the other hand, there is a set of equations called kinematic equations that allow you to distill all the information that's contained in those kinematic graphs uh, into these equations. But you do it with one caveat. The caveat is that the acceleration needs to be constant. So our three equations are here on the left. Uh, they say that the final speed is equal to the beginning speed plus the product of the acceleration and the time. That the distance traveled is equal to uh, the beginning speed times the amount of time that you're looking at, plus 1/2 the acceleration times the square of the time, or that the square of the speed is equal to the square of the beginning speed plus twice the acceleration times the distance traveled. And the variables are listed over here on the right, where Vf is the final speed of the object, V naught is the starting speed of the object, A is the acceleration, D is distance or displacement, and T is time. So how do we go about using these to solve problems? Well, to simplify this, we're going to use an algorithm, and uh, remember that an algorithm is just a set of steps that make a complex that breaks down a complex problem into more simple steps for you to remember. So the first thing we're going to do is we're just going to make a t-chart, and there are 5 variables from the 3 equations. They were the 5 variables on the right-hand side in the previous slide, and you're going to fill those 5 variables VF, V naught, A, D, and T into the left column of the t-chart. Then you're going to look at the problem, and you're going to fill in the right column of the t-chart with the known variables in the problem. Okay, they're always going to tell you 3 of them or assume that you know 3 of them. And when I say they might assume, uh, in a in a vertical situation where something's dropping, uh, the the person that's writing the question might assume that you know that the acceleration due to gravity is negative 9.8 meters per square second, and that probably the object started at rest before it was dropped, so the v naught would be equal to 0. Otherwise, they're going to give you 3 of those 5 variables. Now, sometimes these types of problems can come in two steps. Uh, Sometimes the variables that are given in the problem don't always match up to exactly to what you are trying to find. So if you've got three variables, what you need to do is find an equation of those three that matches the variables you have, and then solve it. Okay, even if it doesn't necessarily answer the question you're looking for. Now, why would we do that? Because sometimes it takes two steps. Sometimes you're going to have to use two equations to find the answer you're looking for. So that brings us to number 5. When you're done solving that problem using the equation that you picked, if the solution to 4 is the answer you're looking for, then you're done. Great, only took one step. But if it's not, what you need to do is use the new variable you just found, pick a different equation that has that variable and two other variables, and look and solve for the one that you need. Okay. Uh, so if you do have something that's basically two of those variables at a time, make sure that you're looking that you get the second one if that's what they're asking for. Thanks. Have a great day, and I'll talk to you later. Please look at my Pixie clips on my BlendSpace site. They give some examples of how do the actual to do the actual problems using this algorithm. Have a great night. Bye.